All right, so we're going backwards in our book a little bit. We're actually going to go back to 6.3, which is volumes using the shell method. So this comes straight after 6.2, which is hopefully something you guys remember and retain from last year. It was about the disk method. So if you look in your book at 6.2 and maybe review a little bit of that, it was finding the volume using the disk method. So this one's a little bit different. It's finding the volume using the shell method. And so essentially what it is if you look in your book on page 427, you'll see this picture. It's a shell, and essentially what happens is this. So it's sometimes can be a little bit confusing with three-dimensional images, just to be able to figure out what they're talking about. So I wanted to show you a little bit about where the shell method is derived from, and then show you how to use it after that. So essentially, you take a piece of your shape, just one piece at a time, like a rectangle like we have here, and you'll have a height to your rectangle and you have a width to your rectangle. Excuse me. And you're going to be rotating it about whatever axis you're rotating it about. So from the middle, right, so in the middle of this rectangle there's this dotted line, and you'll notice that over there on the left hand side they show it by P. So the length from the middle of this rectangle to your axis of rotation, that's P. So that's the average distance, the average radius away from the axis of rotation. And then you'll notice that over here they'll have this P over here. So this is from the axis of rotation to the inner shell, or the inner radius, which is P minus W over 2. It makes sense because half of this rectangle would be W over 2 to get just half of it, and there's two of those. So P minus W over 2 would give you to the inner rectangle, and then on the other side over here to the outer side of the rectangle would be P plus W over 2. So those are just some things you need to look at as far as what it's talking about, and it helps us to figure out where the formula is derived from. So if we look over back at the book, I'll show you some other stuff that we're looking at. All right, so here is how the volume of the shell method is derived. So if you look here, it says that the volume of the shell would be the volume of the outer cylinder, so that would be everything that's inside of that cylinder, minus the volume of what's missing in the middle of it, so minus the hole. And if you go back and look at that picture that we were just looking at it, the outermost cylinder would be with a radius of P plus W over 2, and the inner cylinder would be a radius of P minus W over 2. And so when we do the outer cylinder volume minus the inner cylinder volume, it gives us the volume of whatever's left over. So if you go back to your days in geometry, you'll remember that the volume of a cylinder is pi r squared, so pi r squared, which is this piece here, times h. So essentially it's the area of the circle at the top times the height of the cylinder. So pi r squared, where P plus W over 2 happens to be r. And then P minus W over 2 is the radius in the inner cylinder. So when we multiply all these out, when you multiply out these binomials and you simplify everything, and I would let you kind of prove that to yourself and show you that it works, it equals 2 pi PHW. So P is the average radius. So P is always changing. Obviously 2 pi won't change, but P is always changing because when you take different x values, you're going to have different radius values for that. And then the h, the height, is always changing as well because your function will be at different heights over various times. And then your thickness over here, you're going to have the same thickness of the rectangle every single time because you will choose equal intervals where that's happening. So that's going to be your thickness. So it ends up looking like this formula down here. So the change in volume would be 2 pi times P of y and h of y. Those two are functions of y because they're always changing, times the change in y. And then if you flip over to the next page, 428. Now I'm sorry that I don't have like a printout for you guys to take notes on today. I accidentally left it. So we're just going to have to kind of mosey along and take our own notes on this one. So for this one, it's the actual formula. So it's important to write these ones down, and I would draw the pictures with them just so that you have an idea of what it's actually talking about. Now, the formulas may kind of remind you back to your memory from last year using the disk method, but this is called the shell method. So we're essentially taking this this rectangle and rotating it, however many rectangles we take, and rotating it about the axis to get these different shells. And so we have two different options. On the disk method, there was only one option. You had it perpendicular to whatever axis you're rotating it about. So now, using the shell method, we're actually having it parallel to the axis that we're rotating it about. So here's my rectangle here, and it's parallel to the axis that I'm rotating it about. Same thing, here's my rectangle here, and it's parallel to that axis there. And so write down these two formulas, the volume, and draw these pictures down below, and you can kind of see that you can piece together the different pieces. So from D to C, this is when you have Y values that you're looking at from D to C. And then from A to B, these are when you have the X values that you're looking at. So it just depends what axis you're rotating it about, whether or not you're rotating it around the X axis or around the Y axis. So write those down, and then we'll take a minute to use them in our formulas. Alright, so we're going to do example number 1 together. So it says, using the shell method to find the volume. It says, find the volume of the solid of revolution formed by revolving the region bounded by y equals x minus x cubed and the x-axis from 0 to 1 about the y-axis. So we're revolving it, we're rotating it about the y-axis. So this is going to be a vertical axis of revolution. So I'm going to use the formula for vertical axis of revolution, which is the second one from up above that you just wrote down. Now we'll start writing stuff in just a minute, but I just kind of wanted to show you guys like an illustration of what it might look like. So this this function here is the function we're looking at, x minus x cubed from 0 to 1. And I just kind of wanted to show you some demonstrations of what it looks like to rotate it using the shell method. So I thought that it looked a lot like this one. Now this one, they're actually rotating it around the vertical axis of revolution, just like we're going to be doing in ours. So you can see here, I'll zoom in a little bit. You can see here that this region here kind of looks a lot like the one that we're dealing with, the one that I just showed you here. So they look similar. They're not perfect, but it looks similar. So we're going to look at the animation of the first one is the partition into shells. So let's look at this animation and see what it does. So it's the region to revolve it. We're kind of dividing up our partition into different shells. So in this one, they're looking at 1, 2, 3, 4, 5, 6, 7 rectangles to look at. The one that we're going to do, obviously, is going to have infinitely many rectangles, but this is just showing you what it looks like when you do partition it into rectangles. So this one has 7 rectangles. We're rotating it about the y-axis, about that vertical revolution, and it just shows you what it looks like to rotate one rectangle. Let's see what it would look like to do all of them. So here's your 7 rectangles. There's rotating the first one halfway, rotating the second one halfway, the third one halfway, the fourth one halfway, and the fifth one. And you can kind of see that it starts to come back down again. So it goes up and then it comes back down again. All right, and then if you complete them the whole way, so you can kind of see what it looks like. It goes all the way up to the green one and then comes back down again for the rest of them. So that's kind of what it looks like. It goes up and then comes back down in the middle. And then the last piece, to view the animation of what it looks like here, you can kind of see what it looks like as it starts to form. So this is what we're doing with our formula, is we are forming this shape by rotating it about the y-axis. So you can kind of see it looks maybe like a little bit of an igloo, but it comes down in the middle. So it's a little bit different. It doesn't have that openness in the middle. So hopefully that gave you a good demonstration of what we're doing. We're taking this shape here and we're rotating it around the y-axis. So it should look something kind of like what we were just looking at over there. So let's do the actual work for it. Let me put up some whiteboard space. Actually, let's use paper. All right. So this problem here, for example 1, says to take this line y equals x minus x cubed that I was just showing you on Desmos, and from using the boundary of the x-axis from 0 to 1, you're going to rotate it about the y-axis. So rotate about y. That's at y, but you get the point. About y. So I'm going to look up above at the shell method. I'm going to look at the vertical axis of revolution since I'm choosing the y-axis. So it says that volume equals 2 pi. That's a little different from the disk method. The disk method only had pi. From A to B. So for my x values that I'm looking at from 0 to 1, because it gave me that in the problem. of p of x. And remember that p of x is the length from the y-axis to whatever rectangle you're taking. And so if I can show you a picture, let me see if I can get this picture on here from camera. Let me take a picture of this really quick. This is on page 428 in your notebook, or in your book, I should say. So there we go. So looking at that picture from your book on page 428, you can see that the p of x is this piece here. So it's the distance from the y-axis to the middle of that rectangle, which is honestly just whatever x value you're choosing. So you'll notice that it actually just says p of x equals x, because it's whatever x value that you're choosing. And because we're taking the integral, you could do this by hand and put a finite number of rectangles or a finite number of boxes that you're going to be looking at. But we're taking the integral, so obviously we're taking it at an infinite number of boxes. So your x values will be infinite in between 0 and 1. So it's just whatever x value at that moment is coming up to be multiplied. So that's your p of x. If I keep going in my equation, it's p of x times h of x. And remember that h of x is just the height of your rectangle. So the height is always constantly changing as well, depending on what x value you chose. So the height is x minus x cubed, depending on whatever x value you chose. So that's times x minus x cubed. And then the change in y, remember from the original equation, the change in y is just dx. So whatever your, or change in x I should say, is just dx, whatever your change in x is. So when we go through this, it literally, that's probably the hardest part, is setting it up. From there you just take the integral. So from 2 pi, from 0 to 1 of x squared minus x to the 4th dx. The integral of that is x cubed over 3 minus x to the 5th over 5 from 0 to 1. So that would be 2 pi times 1/3 minus 1/5. And then when you plug in 0, it equals 0. So that's 2 pi times 1/3 minus 1/5, which is 2/15, which is 4 pi over 15. So that's pretty much as hard as that problem gets. Obviously, sometimes they won't be that easy, but for this example at least, sometimes it's nice to be able to use the shell method just because you're able to run it parallel. Those boxes run parallel to the axis of rotation. Let's look at example 2. Alright, so here's example 2. They're saying to find the volume of the solid of revolution formed by revolving the region bounded by the graph of x equals e to the negative y squared and the y-axis from 0 to 1 about the x-axis. So here you can see a picture of that graph. So this is the graph of x equals e to the negative y squared. Now this one would have been a little bit more difficult with the disk method, because with the disk method you would have had to solve this equation for y and get y all by itself. So obviously this is why the shell method is helpful to us, because we don't actually have to go back and do that solving for y in that equation. We can just use the shell method pretty easily to solve for it instead. In this case we're using a horizontal axis of revolution because it's the x-axis now, so we can jump back over to that first formula. So they're saying that the volume equals 2 pi times the integral, this time from c to d because they're y values, so it's still from 0 to 1 on the y-axis, times p of y. Remember that p of y is right over here, and it's just whatever y value you're looking at right now, so that's just y, times h of y. So h of y happens to be the height of that rectangle, and our formula is perfect for us because it's already in terms of y. So they're already giving us h of y in the formula. So that would be times e to the negative y squared dy. And then we're going to have to use u substitution for this. So if you let u equal negative y squared, that means that du would be negative 2y dy. I don't need that negative 2, so I can divide by negative 2 over to the other side. So I get negative 1/2 du equals y dy. So now if I simplify this a little bit, I'm going to change my limits of integration. So if y equals 0, then u would equal, and I'm just plugging it in for your reference, I'm just plugging it in right here to see what it would equal. So if y equals 0, then u would equal 0. And if y equals 1, the upper limit, then u would equal negative 1. And that might give us an issue, and you'll see why. So we have 2 pi times the integral from 0 to negative 1, and then y dy, that's du, e to the negative y squared, that's, or e to the u, because negative y squared is u, du, or I should say negative 1/2 du. So there's two things we got to do. First of all, we got to bring this constant out front, and second of all, we have to flip the limits of integration because we're not allowed to do limits of integration from smaller to bigger, or vice versa, from bigger to smaller. So I'm going to do both of those in the same step. So when I bring the negative 1/2 out front, I get negative 1/2 times 2 is negative 1 pi times the integral, and then I'm going to bring that other negative out front from negative 1 to 0, because I'm going to just flip it upside down, e to the u du. So this is pi, the negative negative makes a positive, the integral of e to the u is e to the u from negative 1 to 0. So this is pi times e to the 0 minus e to the negative 1, which is pi times 1 minus 1 over e, which if you put that in a calculator is approximately equal to 1.986. So obviously the shell method was helpful in this problem because we did not have to solve a difficult equation to get y by itself. We were able to keep it in terms of x, and that really helped us to figure out what we needed to figure out in order to put this into the shell method. So that's perfect. If you look at page 429, it shows you a comparison of the disk and shell methods at the bottom. And so it just shows you when it's helpful to use the shell methods and when it's helpful to use the disk method. So if I can take a picture of that and plot that up here. Let's try and do this. All right, so you'll see this on page 429. So it shows you that for the vertical axis of revolution over here on the first one, we'll have a vertical axis of revolution, and notice how the rectangle is perpendicular to it. That's the disk method. Here we have a horizontal axis of revolution. Notice how the rectangle is perpendicular to it. That's the disk method. So notice here that you have dy and then change in y, dx and then change in x. This one has a vertical axis of revolution and it's parallel to the box, so you have dx with that one. And then this one has a horizontal revolution and it's parallel to the box as well, so that one has dy on that one as well. So you'll just notice that, like, given the information that you're given in the problem, it'll be more apparent as to which one is helpful for actually doing the problem that you're working on. So, for example, looking at example number 3. Let me write that one down. All right, so here's example number 3, which is on page 430. This one shows you both the disk method and the shell method. I'm not going to go through the disk method with you, but I'll show you why it is easier on this one to use the shell method. So if you look at these pictures over here, the top one is for the disk method, the bottom one is for the shell method. So notice that we're revolving y equals x squared plus 1 with the bounds of y equals 0, x equals 0, x equals 1. We're revolving that around the y-axis. So for the shell method, if you notice here, we're revolving it around the y-axis, which gives us nice little rectangles that are parallel to it, and it helps us because our equation is in terms of y equals already, so we know the height already and we don't have to do anything to it. If you look back at the previous one with the disk method, we're revolving it around the y-axis. We have to have these rectangles that are perpendicular to it. In order to find the height of those, however, we're going to need to convert the equation to be in terms of x. We're going to need to figure out what the new bounds are, since x equals 0 and x equals 1. Those are bounds in terms of x values. So that one's just more difficult all around. So if you want to go back and look at that one, you have to break this one up into 2 separate places so that you can find the volume 2 separate ways. That was just all around more difficult. You can go back and look at what they did in the book on page 430 to see how they did that one. But using the shell method, it becomes pretty easy. Volume equals 2 pi times the integral from 0 to 1, because we're looking at the x values, of x, which is p of x, as you can see right here, times the height, which is x squared plus 1, dx. So again, this one became super easy. So it's just 2 pi times the integral from 0 to 1 of x cubed plus x dx. If you integrate that, you get 2 pi times x to the 4th over 4 plus x squared over 2 from 0 to 1. So that's 2 pi of 1/4 plus 1/2. And then the zeros would cancel. So that's 2 pi times 6/8, which if you simplify that, you get 3 pi over 2. So obviously that way is much easier than breaking it apart into two separate things and having to change everything all around. So this is when the shell method would be preferable over the disk method. Sometimes, however, the vice versa happens. So sometimes, however, the disk method is preferable over the shell method. So let's look at example number 4. All right, this is example 4 from page 431. If you look at the picture, you can see that it's a pontoon that's being made in that shape that's on there on the picture. It says it's designed by rotating the graph of 1 minus x squared over 16 around the x-axis from -4 to +4 on the x-axis. So on this one, we're rotating it about the x-axis. So it would have been really helpful if everything was in terms of x with limits on y. So if this was solved already for x and this had limits on y, that would have been really helpful because we could have jumped straight into the shell method. But knowing that we have it in terms of y equals 1 minus x squared over 16, it's not as easy to use the shell method because you'd have to solve for x and it would just take a lot of work and it wouldn't be very easy to do that way. So instead, sometimes it's easier just to use the disk method. So just a quick little review of the disk method. Hopefully this helps to spark your memory. The volume using the disk method is pi times the integral from -4 to 4. So similar so far. It's not 2 pi, it's just pi. And then you have the function 1 minus x squared over 16 squared dx. So that's the volume, remember, using the disk method. So if you square all this out, I'll jump ahead a few steps, but you get pi from -4 to 4. If you square all that out, you get 1 minus x squared over 8 plus x to the 4th over 256 dx. And you can always check this just to make sure it's making sense to you about where I'm getting these things. Which, if you integrate that, you get pi times x minus x cubed over 24 plus x to the 5th over 1,280 from -4 to 4. Which, if you plug everything in, you get 64 pi over, over 15, which is about equal to 13.4 feet cubed. So the disk method in this case was easier just because it was already given to us in terms of y, and we were rotating it about the x-axis. So sometimes it's easier to use the disk method, sometimes it's easier to use the shell method. In the next example that we're actually going to do, you're going to see that it's actually necessary to use the shell method. So let's look at example number 5. All right, so here is the last example, which is example number 5. We're trying to rotate y equals x cubed plus x plus 1, which you can see in this picture, with the bounds of y equals 1 and x equals 1 about the line x equals 2. So we're rotating it about this line here. So we're not rotating it about one of the axes anymore. We're actually rotating it about this line. So in this case, it's actually essential and necessary to have the shell method because, as you can see, we have our little rectangle. It's in terms of y already, which is good because we're trying to rotate it about the y-axis. It's in terms of y. And you can't actually solve for that in terms of x easily at all. So this one would be necessary to have the shell method. So yeah, because you can't easily solve for y in terms of, or vice versa, you can't easily solve for x in terms of y, this one definitely you needed to use the shell method for. So you wouldn't have been able to do this one using the disk method beforehand. So we're going to have this vertical rectangle that is parallel to our axis of revolution, which is x equals 2. So because the axis looks like this, we're going to have the shell method around the vertical axis. So it's 2 pi times the integral, which the bounds on this integral are going to be from 0 to 1, because we're looking at those bounds on the x, which are from 0 to 1. And then we have p of x, which normally p of x is just x, but if you look closely here, let me erase some of this stuff. If you look closely here, p of x is now 2 minus x, because we're working backwards. So we're looking at the interval from 0 to 1, and we're revolving it or rotating it around x equals 2. So we're actually going backwards from 2. We're subtracting different values of x to get back to these different rectangles that are in our interval over here. So it's actually 2 minus x for p of x. And then the height h of x, which is just the formula that we have over here. So x cubed plus x plus 1. All right, and then we actually have to subtract 1 from that because if you look closely at the picture right here, we don't want any of this volume here. So we have to lower that down back to where we want it on the x-axis. So we have to subtract the 1 that we pushed it up so that we can bring it back down to the x-axis because we're actually not looking at that volume. And I knew that it was going to be 1 because it specifically says in the original problem that it's bound by the line y equals 1. So that tells me that I needed to subtract 1. Dx. So if I simplify all this and multiply it out, I get 2 pi times the integral from 0 to 1 of negative x to the 4th plus 2x cubed minus x squared. And again, you can verify this, plus 2x dx. So when I integrate that, I get 2 pi, and then that integrates to negative x to the 5th over 5, plus 2x cubed integrated would be 2x to the 4th over 4, which is x to the 4th over 2, minus x squared integrated is x cubed over 3, and then 2x integrated is just x squared. And that's from 0 to 1. So when I plug in 1 to these, I get 2 pi times negative 1/5 plus 1/2 minus 1/3 plus 1, and then the zeros will make it all go away. So when I finally simplify this, I get 29 pi over 15. So this one, obviously, the shell method was necessary, for sure necessary. I'm going to highlight in purple just a few things that we did differently in this problem that we didn't do in the other two, and how you know to do them. So remember, this one was a little different because we were rotating it about the line x equals 2, I'm sorry. So it wasn't along the line, the y-axis. It was also a little bit different because we weren't closing it on the boundaries. So normally we close it on the x or y-axis alone. On this one, because we weren't, we actually had to account for that here by subtracting that 1 because of this cap here. All right, so that helped that, and then the line, rotating it about the line x equals 2 helped us to do the 2 minus x piece. Those were really the only things we changed, so that's really all you have to look at for that, and that's it for today. And that's actually all of 6.3, so we covered 6.3 just in one day.